So let me just start. So this course has been primarily about metal oxides, and we are going to be looking at a few applications of these metal oxides. Of course, the focus is on using these metal oxides as gas sensors, which is what Professor Celso has been talking about, starting from yesterday and continuing today and tomorrow. But from my perspective, I thought I will just tell you briefly why we are interested in these oxides and what really we are using them for. We also do some work with gas sensors, but I would not be really talking about it because that's what Professor Celso would be doing. But I like to focus a bit on what we want to do with these semiconductors, which is primarily for transparent applications, and also tell you a bit about some of the work that we do with using or doing color changes in these semiconductors. So the title is transparent semiconductors, but more importantly we are actually looking at transparent conductive materials or transparent conductive electrodes. So how do we want to describe these? So we are interested in materials which have high electrical conductivity. So basically they allow charge carriers to flow through. They can be electrons, holes, at this particular point we don't care. We just want high electrical conductivity. But more importantly, we also want good optical transparency, right? We want these electrodes to be invisible to us, so essentially we can see through them. There are a variety of materials that do this. Initially we are going to be focused on oxides, but I will also tell you some of the work that we do with silver nanowires, which also satisfy these criteria. So here is a plot of transmittance versus sheet resistance. So if I want a material that has good electrical conductivity and good optical transparency, ideally I should be in the top left corner of this plot. So top left corner essentially means my sheet resistance is very low. At the same time my transmittance is also very high. Just as a frame of reference, you see, let me just erase this. You see glass has been marked here. So this is typically your quartz. Think of the quartz slides, the slides that you use in a lab. This has a transparency of around 95%. If you just took pure quartz, put it in a UV visible absorption system and just looked at light going through, we have a transparency of around 95%. So anything that I deposit on glass will obviously have a transparency less than that, right? We can never exceed 95% because that is the limit set by the glass. So we ideally want to be as close to 95% as possible, but at the same time we realize that there will always be scattering at interfaces, so the values that we get are slightly lower. How do we achieve this? So how do we achieve both good electrical conductivity and good transparency? There are two strategies. The first strategy is you take something that's transparent and then you do something to improve the conductivity, right? So you go from two extremes. You start with a transparent material, and typically that is a semiconductor, and then you try to do something to the semiconductor, usually that is doping, in order to improve the electrical conductivity. And classical examples are of course indium tin oxide, aluminum doped zinc oxide. Usually a lot of oxide based materials are used for this. There are some drawbacks of course. Usually oxides are ceramics, so they are brittle in nature. The other strategy is you start with a conductive material and you somehow improve the transparency of the material, and we will talk about it later, but that is approaching the problem from the other side. So instead of a transparent material, you start with a conductive material and you improve its transparency, and this is usually done by using metals in the form of nanostructures. So let's look at the first approach. That's where transparent conducting oxides, usually people also call them TCOs, come into picture. Where would I use these TCOs, or where would I use transparent materials? There are two applications that people normally look at. Both are essentially optoelectronic devices, so devices which combine electrical properties with optical properties. The first, of course, is a light emitting diode, LEDs. People also work on organic light emitting diodes, so OLEDs. So most of our displays that we use, so whether it's a smartwatch or for a smartphone, a tablet, a laptop, even a TV, all have displays that are made out of LEDs. LEDs essentially have a whole transport layer, an electron transport layer, there are emitting layers, but ultimately somehow I must let charge carriers reach these layers so that I can have a light that comes out. So any important part of an LED would be the TCO layers, which is the transparent conducting oxide layers. In the case of an LED, we are putting we are sending in charge carriers, we are sending in current, and we are getting out light. The reverse, of course, is also very important, and these are your photovoltaics or solar cells. So these are materials that absorb light. Typically the light is in the UV and the visible region, and then that generates charge carriers which we can use for any purpose. So these materials also have TCOs. So essentially they also have these transparent conducting oxides. So these are of course the two most common examples where transparent oxides are required, but of course there are a variety of other examples as well where people use TCOs. Whenever we think about TCOs, indium tin oxide is probably the most widely recognized and the widely used TCO commercially. ITO is nothing but indium oxide which is doped with tin, and we will see the reason for doping in a minute. So almost all smartphones essentially have an ITO layer at the top. They are not necessarily part of the display in the sense that they are not the active display layer, but they are the layer that enables us to do touch work or touch enabled access to the smartphone. If you want to look at the transmittance of ITO, so this is just a commercially prepared ITO film. Most of the time indium tin oxide is made by sputtering. So you start off either with an oxide target or you start with a metallic target and sputter with oxygen. People also do PLD, pulse laser deposition, is another way to deposit ITO films, and of course there are other wet chemical routes, sol gel routes, spray pyrolysis. There are a variety of other techniques, but commercially when people make ITO films, it's usually by some sort of a physical vapor deposition process. So this is just a transmittance of a sputtered ITO film. So again for reference we have quartz, and quartz is somewhere around 90-95%, and here you see that ITO itself has a very good transparency in the visible region. It's somewhere around 80%. The transparency is also pretty good in the IR region, but drops in the UV region simply because there is a band gap. So ITO starts absorbing light to promote charge carriers, but essentially the visible region is what we are interested in, and that's the region where we want to establish the transparency. So just for us to understand what sort of properties we are looking for our semiconductors, I'll just pull back a bit and then just tell you something basic. We are of course all familiar with the electromagnetic spectrum. It goes from a wide range starting from gamma rays X-rays, UV, IR, microwave and so on. This of course is the higher energy or the lower wavelength, and this is the lower energy or the higher wavelength regime. What we are interested in is the visible region. The visible region typically extends to between 400 to 800 nanometers. Below 400 we call it UV, above 800 it's IR. If you want to convert this into energy, you just do hc by lambda. So E is just hc by lambda. We can get the energy as well, and the energy range is from 3.1 to 1.6 electron volts. So if somehow I have a semiconductor whose band gap is more than 3.1 electron volts, which means any light whose energy is less than 3.1 is not going to be absorbed, it is going to pass through the semiconductor, and then we say that the semiconductor is transparent to that particular light. So as long as I have a starting material whose band gap is greater than 3.1, then I have a transparent semiconductor. So that's why usually people say that 3 electron volts is the boundary between semiconductor and insulator. Anything that's more than 3, 3.5 is are called insulators. Of course, there are exceptions to this rule. So that is good. All I need to do is to find a material whose band gap is greater than 3.1. The issue of course is that the moment I have a large band gap, my carrier concentration is also low. So if you remember, this is from a couple of classes ago, we wrote this exponential minus Eg by 2 kT. If my Eg is high, then obviously my Ni is low, and if my Ni is low, my charge carriers are low, then I don't have good electrical conductivity, right? We said we want both transparency and electrical conductivity. Transparency I am able to achieve by having a higher band gap, but obviously that's also going to affect my carrier concentration. So we need to do something else, and usually that something else is you dope so that you create extra charge carriers in your semiconductor, and that allows it to be conductive. So when we come to ITO, we say that the starting material is indium oxide. Indium oxide is commonly found in the cubic phase. There is a particular name for it, and there is also the crystal structure of indium oxide, where red represents the indium and white is oxygen. The band gap of indium oxide is around 2.7 electron volts, but interestingly you can see that there is an optical absorption at around 3.7 electron volts. So in a way this is slightly contradictory, because we have been led to understand that whenever we have a band gap, that also means you can have optical absorption at that energy, but the optical absorption in indium oxide is slightly higher. That makes it a material that's transparent to visible light, because the absorption only happens at 3.7 eV, and we said that 3.1 eV and below is visible. These are just some single crystals of indium oxide, just showing you that they are transparent. So for a long time people thought that the reason why indium oxide has a band gap of 2.7 but an optical absorption of 3.7 is because at 2.7 eV it is an indirect band gap transition, and so the direct band gap is 3.7. So I think someone yesterday was asking about indirect and direct band gap transitions. So that was originally the thinking, but newer studies basically show that that's not really the case. They are still a direct transition, So in this particular diagram, this is the band structure. So the 0 represents the valence band maximum, so the maximum point in the valence band. The 3 here basically represents the conduction band minimum. So this gap from 0 to 3, so this red dot is essentially 2.7 eV, but because of some dipole restrictions, optical transitions cannot occur within these two regions. So there are some forbidden optical transitions, so we will not go into really the details. I think that's more to do with the particular arrangement of the valence band states in indium oxide, which means that for an optical transition, for an electron to jump from the valence band to the conduction band by absorbing light, it only happens from a state that is slightly into the valence band. So this energy gap is around 0.8 eV, I think that's what's written here, which means for indium oxide to absorb light and for electrons to go from valence to the conduction band, you need to supply 2.7 plus approximately 0.8. That gives it a larger band gap, which is why it is transparent it is transparent to visible light. So this is the band structure of indium oxide, but the problem of course is indium oxide is not very conductive. So we need to somehow improve the conductivity, and that's where doping essentially plays a role. So again, I think yesterday as part of the defects, there was a question as to whether defect engineering is good or do we need to do other things. We can create defects to some extent, especially when we talked about zinc oxide, we talked about oxygen vacancies and so forth. But if you want really high conductivity, you need to add some other material to your oxide. So doping is usually the more preferred route in order to improve the electrical conductivity of the semiconductor. So tin doped indium oxide has a general formula IN 2 minus X, so SNX. So it is nothing but the substitutional doping of indium by tin. So wherever we have indium atoms or indium ions, you replace it by tin. Typically people find that around 8 weight percent or 7 atomic percent of tin is sufficient in order to give us good electrical conductivity. To understand what happens, we just look at the oxidation state. So indium is in the +3 oxidation state. If I were to replace an indium by tin, so tin is in the +4 oxidation state. So when we do this, in order to maintain the charge neutrality, we need excess electrons, and these excess electrons are essentially found in the conduction band. So the defect state is a state that is close to the conduction band edge, so that thermal vibrations are sufficient to excite those electrons to the conduction band, so that we have free electrons in the conduction band. When we dope tin with indium oxide, we form what is called a degenerate semiconductor. In the next slide I will tell you a bit about degenerate semiconductors. It's something we have not talked about earlier when we did extrinsic semiconductors, but I'll tell you what it means. So overall, the band gap of the material is still high. It's a wide band gap 3.6 eV, which essentially means it's transparent to visible light. At the same time, the presence of tin gives you extra charge carriers so that you also have good electrical conductivity. Again, this is just a band picture showing you both indium oxide and indium tin oxide. Because of the presence of your tin, you basically have some extra electrons that are present in the bottom of the conduction band. Papers also refer this as something called a Bernstein-Morse shift, which says that the optical gap increases because of the presence of electrons in the bottom of the band. So if I want to have a transition, electrons from the bottom have to actually jump above these filled states. So when you do optical measurement, you will actually see a shift in the band gap. It's not necessarily a change in the band gap itself per se, but it is because I have filled states in the bottom of the conduction band. I actually have to go to a higher energy state, and that is seen as a shift. So either way, ITO is an n-type semiconductor. I think I didn't write it down, so I'll write it down here. So it's an n-type semiconductor, and it's also a degenerate semiconductor, which allows it to have good electrical conductivity, at the same time good transparency. So just to tell you what a degenerate semiconductor is, I'll probably go back to extrinsic semiconductors. So we saw extrinsic semiconductors mostly in the context of silicon. So we either have n-type semiconductors or p-type semiconductors, and these are defect states. So these are your donors, which are located close to the conduction band, and these are acceptors, which are located close to the valence band. Now if you see this diagram, this is something pretty interesting. I think given the fact that this is a short course, no one really picked it up. If you see the conduction band, it is drawn as continuous. We draw lines to show that it is a continuous state or an extended state. But if you see the dopant levels, they are just drawn as individual dashes, right? We don't draw a dopant line, we just draw them as just dots or dashes. The same way here, we also see the boron states. We only draw them as dots, we don't draw an extended impurity state. And the reason is most of these states are localized because of the low dopant concentration. So just to put that in perspective, let us say I have silicon, the same is true for germanium or gallium arsenide. We saw that pure silicon is intrinsic, and to improve its conductivity we either dope it with group 5 elements to make it n-type, or we dope it with group 3 elements like boron to make it p-type. The question is how much boron or how much phosphorus should I add to silicon, right? Because from a practical point of view, we want to know what is the dopant concentration. We saw that we could do doping is usually a high temperature diffusion process, but we never really asked how much boron or how much arsenic or how much phosphorus should I add to my material. Turns out typical dopant concentrations are very small. So ppb is parts per billion, so it's around 10 power minus 9. ppm is parts per million, so it's around 10 power minus 6. So that is typically the dopant range. What it means is that let us say I have parts per million, it means that I have 10 power 6 silicon atoms, so 1 followed by 6 zeros. I have so many silicon atoms, I replace one of those with boron or phosphorus, right? That's what parts per million means. Out of 10 power 6, I am only replacing one. Because I am doping such a small amount, my dopant levels are all individual energy levels. They are not a continuous, that is why we show them as dashes. They are all individual energy levels, either located close to the conduction or the valence band. And again, because I am adding such a small amount, I am not changing the lattice parameter or the band gap of my material, right? So those parameters are not being changed. I am only adding these to change the electrical conductivity. Now if I keep on increasing the dopant concentrations, if I move beyond this limit, ultimately these individual energy states will come together to form a band, So here in this case, at higher impurity concentrations, the impurities come together to form a band, and if this band is located close to the conduction band, I would have an overlap of the impurities and the conduction band, and that will give me a degenerate n-type semiconductor. The same thing happens if I have lot of acceptors. The impurity band of the acceptors will merge with the valence band, so again I have a continuous band. So when we have this situation, when the impurity forms an energy band, and typically for silicon you can do the math, somewhere around 10 power 19 per centimeter cube, or maybe at around 0.1% of dopant concentrations. So this is 10 power minus 6, so I am looking at 10 power minus 3, so 3 orders of magnitude more. You will find that the dopant energy levels merge with the conduction or the valence band, and you have what is called a degenerate semiconductor. Interestingly, such a semiconductor behaves as a metal. What it means is that the electrical conductivity, so sigma, reduces as temperature increases. So normally when we talk about semiconductors, we said that the conductivity increases with temperature, but a degenerate semiconductor is one where sigma actually reduces, because I already have a very high charge carrier concentration, that is not going to change, but obviously I will have more scattering, mobility will go down, which means sigma will go down. So that is why we say this behaves as a metal. So the same concept is valid in indium tin oxide. When I dope tin with indium, we have such a doping concentration that the impurity levels of tin merge with the conduction band of the indium oxide. So essentially I have a degenerate semiconductor with a large carrier concentration. I also have a wide band gap, so it is transparent to visible light. At the same time, it also allows charge carriers to flow. The ITO of course is one particular oxide, but one of the drawbacks now especially is indium is expensive, it is very hard to get indium. So people are looking at a variety of other materials. Zinc oxide based TCOs are particularly popular because zinc oxide is widely available and used. So aluminum doped zinc oxide, so that is marked here, it is also called AZO. It is one particularly used oxide. Instead of ITO, people also use FTO, so that is fluorine doped tin oxide, that is again a widely used TCO. So there are a lot of people working on trying to find other n-type transparent conducting oxides. If I can have an n-type oxide, then obviously I should be able to have a p-type oxide as well. So there is work on p-type TCOs as well. So now remember, so this should be a material where I have more holes than electrons, which means I should have defect states that are located close to the valence band of the oxide, and if I want this to be degenerate, then again I want these defect states to overlap with the valence band of TCOs. For normally oxide materials, the valence band is made up of the filled oxygen 2p levels, and these are usually localized in nature. So again people, by looking at first principle calculations, they have figured out that you need a extended valence band, especially if I want to make TCO, because we want the holes to be able to flow through your material and not be at localized states. So one popularly used type of TCO is copper based. So it is of a form copper. M here stands for metal. The metal can be aluminum, gallium, indium and so on. So there are different types of these materials which are called delophocytes, that is a general term for them, where the hybridization between the D10 shell, so this is the closed shell of copper, and the oxygen generates an extended valence band which allows for charge carriers to move within the semiconductor. So these are then doped. So this doping introduces additional holes in the material. So essentially you can make p-type TCOs. At least from my understanding, the p-type TCOs have not reached a stage that is on par with either ITO or other n-type TCOs, but there are active research going on in this area. So just to sort of give you again an idea, so this is a plot of transmission, but now this is inverse sheet resistance, so 1 over the sheet resistance. So if you want to be a good material, now you should be in the top right corner, because this is inverse sheet resistance. So this is low value of resistance, so low rho, and then this is high. So you should be somewhere here, and if you look at ITO as the benchmark, so you are somewhere here with a transmittance of greater than 85% and a very low sheet resistance. There are a variety of p-type materials that are being investigated, but again the issue is how do I square the transmittance with the sheet resistance. So that again is an active area of research. If you are really able to get a good p-type TCO, I have an n-type TCO, I have a p-type TCO, then I can start making devices, transistors, diodes and other sorts of devices. So essentially there is a whole branch of transparent electronics that people are working on and that you can develop commercially. So far those were about trying to make semiconducting oxides that are transparent, but I also thought I will tell you briefly about some oxides that can also be used for imparting color, and these again have some applications in displays. Another reason for picking this out is, again, this is a topic that we work on, so I thought I will also give you a flavor of some of the research that we do, especially given that most of you here are graduate students. So I want to talk about what are called electrochromic materials. So chrome essentially refers to color, and these are essentially materials that change color because there is a change in the oxidation state of one of the materials in the oxide. So usually it is the metal, so it's a change in the oxidation state of the metal which causes a change in the color. Again, there are a variety of materials that are researched and that are being used. You broadly classify them into two types. You have what are called cathodic coloring oxides. So these are transparent when they are in the oxidized state. So essentially at the higher oxidation state they are transparent, and to color them you need to reduce them. So you need to go from a higher state to a lower state. Tungsten oxide is an example of this, I will show you in a minute. We can also have the opposite. These are anodic coloring oxides. So these are transparent in the reduced state, which is a naturally occurring state, and then you need to oxidize them in order to color them. So either way, whether I have a cathodic coloring oxide or an anodic coloring oxide, you need metals that can exhibit and that are stable with multiple valence states. So usually these are all transition metals. That is why you see that almost all the metals that are investigated or used for this purpose lie in the transition metal region. So where do we actually use EC films? One of the most common application are what are called smart windows. So these are essentially windows. So in this particular example you see a region that's transparent, but by applying a voltage I can make it colored, and by making it colored you typically turn it opaque so it blocks the light. And again this is another example of a window that can be made opaque. There are some more examples. For example, you can think of your rear view mirror of a car, or even the case of an aeroplane. And again this is something that's already there, so you can change the tint in the window by applying a voltage. So you can go from being completely transparent to being semi transparent to being fully opaque. There's also some other research where people have tried to use EC films for displays. There are applications for sensors. So I'm just giving a small snapshot of some of the applications of these materials. So let's start with tungsten oxide. I told you tungsten oxide is a cathodic coloring film. So tungsten in the natural state is +6, so WO3. So essentially I have tungsten +6. If I were to react it with electrons, so I am essentially reducing it. I go from +6 to the +5 oxidation state. So here the transformation is not complete, so that's why we write it as tungsten +6 1 minus x, tungsten +5 x O3. So this is now a colored oxide. It has essentially a deep blue color, and importantly this reaction is reversible. So I can go back from my deep blue to the transparent state. So essentially I can switch between these two states. Just to show you how such a device would look, so this is a very simple schematic that says that I have a transparent conducting glass over which my tungsten oxide is deposited. So this region is WO3, and then when you apply a potential, electrons will travel in the external circuit and basically cause a reduction. Within the device itself, to balance charges, there are going to be counter electrode and ions. So positively charged ions will also move and intercalate with the tungsten, so that would put it in the reduced state. And the reverse happens. So when you want to go from colored to transparent, you need to reverse the polarity so that the electrons go out and the intercalated ions would also go out. Typically the counter ions used are either H plus, depending on what electrolyte you use, or it could be some sort of a lithium based electrolyte, in which case it is lithium plus. So again there are some parallels with solid state batteries, because there in batteries also we look at lithium ions essentially moving from the anode to the cathode. So electrochromic film, so even though it is actually based on one particular material, is a multi-layer device, and I'll show you the device structure in subsequent slides as well. So you need some sort of a transparent substrate, usually that's glass. You need to have charge carriers move in and out, so I need some transparent conductors. Typically they are ITO or FTO, so essentially transparent metal oxides. You have an ion storage or the electrochromic film. Then you have an electrolyte, which is usually a solid state electrolyte, because you want this to work in the solid state. Then you have electrochromic film again. So you can see that the device is symmetric about this electrolyte, right? So there are two layer active layers, which is the electrochromic film, and I'll tell you what they are. Then I have a transparent conductors and I have a transparent substrate. So it's essentially a very symmetric device. So in our group, this is one of the reasons why I brought this up. We work on tungsten oxide. These films are grown by reactive sputtering. So you have a tungsten target which you sputter with in the presence of oxygen and argon. So essentially you can grow tungsten oxide film on your substrate. In this particular case, the film is taken in an electrolyte, so that when we apply a potential, we can see the color change. So this is actually work done by one of my postdocs, Dr. Sudha. So she is also here as part of the class. So any questions, you are welcome to ask her. I think she's sitting at the last. So this is just a video showing the electrochromic change in tungsten oxide. So initially the film is transparent. So as you change color, you essentially go from being transparent to opaque, right? So you can see the dark tint. It depends on how complete the transformation is. If the transformation is not 100% complete, the color will not be completely opaque. So that also actually gives you a handle. And then when you scan back again, you can go back to transparent, and this is a process that you can repeat. What really happens when we look at the band structure of tungsten oxide? So typically tungsten oxide, you think of it as you have a valence band and you have a conduction band, and as deposited tungsten oxide is transparent. When you do this intercalation process, so when you reduce your tungsten oxide, you are essentially pumping electrons into the system. So these electrons occupy the conduction band, and they prevent this transition, which means the transition now has to happen to a higher energy state. And higher energy usually means you are going towards the blue end of the spectrum, which is the reason why you have a blue color. And this diagram shows you that when you go back, you would not essentially go back to the original state, but there is always a small amount of electrons still left because the bleaching process is not 100% complete. And if that happens, then there is a slight shift in color as well. So essentially how well you populate your conduction band sort of defines what sort of color that you will get in your final device. Tungsten oxide is an example of a cathodic coloring oxide, which means we go from a higher oxidation state to a lower oxidation state. We can also do the reverse, and this is again work that we did in our group, where we start with nickel. So we have nickel oxide, and we can grow this nickel oxide by sputtering. We can also grow this by solution routes or chemical reduction techniques. So we have nickel 2 plus that's transparent. From there we go to nickel plus 3, which is a dark brown state. So now we are actually going from a transparent state to a colored state by changing the oxidation from plus 2 to plus 3. So in a way this is complementary to tungsten oxide, where there you go from transparent to colored by going from plus 6 to plus 5. So you are going down. Here you are essentially going up. And again we have done some work with nickel oxide, again in electrolyte, where we can see that we can cycle from these two states, and we can do this multiple cycles. We can also measure the time of these transitions, and typically this happens within a couple of seconds. So they are fast, but maybe not as fast as say an OLED device, but the advantage is these are typically single layer devices, so they are a lot more cheaper and consume much less power than say an OLED device. So I have now tungsten oxide, which is an anodic coloring oxide. I have a nickel oxide that is tungsten oxide is a cathodic coloring, while nickel oxide is an anodic coloring, which means I can put both of them together and actually fabricate a device structure. So this is a typical structure that we fabricated. So now I have a substrate. The substrate is just glass, over which we have FTO. We normally just buy these FTO coated glasses, so they are available in the market. On one of them we have deposited nickel oxide. On another substrate we deposit tungsten oxide. We want to show that this works in the solid state. So we have a solid state electrolyte which is essentially a gel which is PVA with phosphoric acid. So we can just sandwich these two devices with the PVA to essentially make a solid state device. And this video here is the solid state device which we are just powering by shining light. And again you can see that when you scan, you go to a very dark opaque state, and then I can scan in the other side and make it transparent. I can also scan it such that the nickel oxide changes color, and that's what you really see, that sort of a bleached color there. So and this of course is repeatable, so I can scan multiple times and essentially have a solid state device. Once you have this basic structure and you optimize this, you can do lithography, which means I can do patterning, so I can make some sort of a display. Interestingly, tungsten oxide is also a very good gas sensor. So now the question is, can we have a gas sensor and an electrochromic film, so that you could have some sort of a visual indicator of whatever gas you are sensing. So essentially you are building a display unit integrated to a gas sensor. So those are some things that we are working on. But let's again go back to the general topic. We said that we are interested in transparent conducting electrodes, and we saw one strategy, which was you start with a transparent material and do something to improve the conductivity. That's what we were been looking at so long. We looked at ITO, that was an N-type, then we looked at P-type TCOs and so on. I can also start with a conductive material and do something to improve the transparency. So normally when we think about conductive materials, metals are the ones we think about. So these could be silver, gold, copper of course is the most well known conductor. The problem of course is metals are all opaque, right? They don't allow light to pass through. So one way to improve transparency is to actually make very thin metal films, so somehow reduce the thickness of the metal, and typically if the thickness of the metal is less than 10 nanometers, you can get some measurable transparency in these materials. So how you do this, what are the strategies to grow ultra thin metal films, is again not something that's very easy, but people are working on that. The alternate is to have some sort of an incomplete structure. So essentially it is a structure with a lot of pores. So if you want to think about a metal mesh, so maybe I'll just use this space here. So think of these as lines. So these are lines of metal, so this is nothing but a mesh. So these lines allow current to pass through, but all the regions which are uniform, where there are no metal, you can also have light passing through. So another way of getting transparency is to make metal meshes, so that the current passes through the metal lines while the gaps in the mesh allow for light to pass through. But fabricating these meshes typically again involves lithography, because you need these lines to be like tens of microns in thickness. So those are harder to do. So in our group what we do is to actually have metal nanowires, and typically we do this with silver, because silver has a very good electrical conductivity, it is stable, and we can synthesize nanowires quite easily. So I have again a random mesh of metal nanowires. So think about this, but now you think about a more random arrangement of wires. So once again, wherever the wires touch each other, so for example if I have current, I can see that there is a current path that goes from here to here. So I do have electrical conductivity through the network. At the same time I have a lot of gaps in between the wires that allow light to pass through. So by using a random network of metal wires, once again we can achieve both conductivity and transparency. How do we make silver nanowires? There is a very standard process called the polyol process. It is again a wet synthesis route, something that we have been working in the lab. So you start off with silver nitrate, reduce it in the presence of PVP. So that essentially gives you silver nuclei. These nuclei act as the seed for growing these nanowires. We use FeCl3 again as a stabilizing agent, and we can control this process, essentially the temperature, the time, and so on, so that we can get silver nanowires. In this particular example, we have nanowires that are around 10 to 12 microns long. Diameter is less than 80 nanometers, and currently we are optimizing this process just so that we can get wires that are 100 microns long with diameters of maybe 100 to 200 nanometers. So we can get really long wires with small diameters, and the good thing is the longer the wire, usually better is the transparency. Once you have nanowires, how do we essentially deposit them? Because I need to get them on a substrate so that I can do make a device. There are various techniques that people use to sort of get uniform films. These are rod coating, spin coating is something that's very commonly used. I'm sure most labs have a spin coating system. You can do screen printing that allows you to make electrodes, especially for solar cells. When people talk about silver electrodes, they do those by screen printing, but those are silver nanoparticles, not nanowires. You could do brush printing, spray coating, roll to roll fabrication. So a variety of techniques are available. Unfortunately, all of these techniques, if I want to make pattern films, we do need additional steps. So some sort of, either you need to do lithography steps, or in the case of screen printing you need to have a mask that allows you to make pattern deposition. So in our group we have a direct writer system. So essentially it is a form of additive manufacturing that allows you to deposit these silver nanowires or any other nanostructures at specific locations on the substrate. The material is taken in the form of an ink. So these nanostructures are dispersed in some solvent where they are stable, and this is then deposited on the substrate at the specific location. I know some of you have wanted to visit the lab and see your facilities, so at that time we can also show you our direct writer system. So we've been talking about transparent materials, so whether it is semiconductors or metals, and we said that these should have two important parameters, right? We should have both transparency and you should have conductivity. Now the question is, I may be working on silver, someone may be doing work on ITO, someone else may be working on graphene. So how do you sort of compare which films are good, right? So ultimately that's what the market wants. Given other growth parameters, people would like to know which film is good. Now we have two values that define your film. You can do transparency measurements. For example, you can do UV visible spectroscopy and report the transparency. Usually this is reported in the middle of the visible spectrum, so at 550 nanometers is where you measure the transparency. You can also measure sheet resistance, so that will tell you the conductivity. So normally we want to combine both of these into a single parameter. The most commonly used parameter is called the Hack figure of merit. So Hack is just again the name of the person who came up with this. There are other formulations also available, and recently we have been seeing groups that use some of these other terms, but essentially the Hack figure of merit is probably still widely used. So this is nothing but the transparency raised to the power 10 divided by the sheet resistance. So if I have a film, I do UV visible spectroscopy, I know the transparency. I measure the sheet resistance, so I know RS. So T to the power 10 divided by RS gives me a figure of merit. Higher the value of this figure, obviously better it is, because this is higher because either the transparency is higher or even and the sheet resistance is lower, and that's really what we want. So I told you about silver nanowires, just to give you an example of some numbers. So we measured the sheet resistance of some of our printed nanowires. So typically you can see sheet resistance is around 30, depending on how much silver we have, it can go from 30 to something like 10 or even 5 ohms. Obviously the more silver we have, the more scattering we have, so lower is the transparency. So we need to sort of adjust these two things, the transparency and the sheet resistance. And this is just a picture showing a fabricated device. This is on PET, so it's a flexible substrate, and you can sort of clearly see through it. So we can calculate the figure of merit. For reference, here is ITO, which is prepared by a pulse laser deposition process. It has a transparency of around 87%. Remember, glass is 95, so ITO is pretty good. It has again a very low sheet resistance of around 35, so that gives you a figure of merit of around 7.1. So you just do 87% is 0.87, so 0.87 to the power 10 divided by the sheet resistance. In the case of silver nanowires, we not only looked at stuff that we did, so this is from our group, but there are other groups that work on silver nanowires, and typically you can see that most people achieve a transparency of somewhere between 80 to 95%. So already in terms of transparency, silver nanowires are comparable to ITO. The sheet resistance values are again more or less widely changed, but they are all well below 100 ohms, which is again sort of a benchmark that people look at. So most people are able to achieve a figure of merit that is better than ITO. So silver nanowires, they are comparable to ITO in terms of figure of merit. They have an added advantage in the sense that they are flexible. So if I were to drop an ITO film, it would break simply because ITO is brittle. Silver being a metal, that's not going to happen. In fact, we have done experiments where we have bent the silver, twisted it, and nothing really happens. The device works really well. But of course there are some drawbacks. One of the drawbacks is, remember, it's a nanowire network, so there is always some non-uniformity in the film, and especially when you have Joule heating, there are local hotspots that are created in the silver, and this can essentially cause local degradation. So especially if I am making a device where I have organic layers and I have local heating, that can affect the organic layer, and that can degrade the whole device. So how do I get some sort of a uniform heating in the silver nanowires is a challenge. So one of my students is working on that. The other big issue is roughness. Because these are wires, so if I have a wire of 100 nanometers, then typically I am looking at a roughness which is equal to the diameter of the wires, because think of a substrate in which I have a wire and I measure the overall roughness, then obviously I have this hump of 100 nanometers. ITO on the other hand, which you grow by say PLD or sputtering, can usually give you very uniform layers which are less than 10 nanometers rough. So if I want to make a multi-layer device, having a very smooth film is essential, because then I can build the subsequent layers. Doing this with nanowires right now is still an issue. It can be a top layer, but trying to build devices with a silver nanowire layer as the bottom is still challenging. So again we are looking at, can we make composites so that the overall composite film has lower roughness, and what sort of roughness values that we can achieve, those are challenges. But essentially if you can tackle some of these challenges, it is possible to actually have silver nanowires as an alternate layer to ITO. And interestingly, it has not been done. If I remember right, I think at least a few months ago I did remember reading an article where your cell phone screens, at least some of them, they are replacing ITO with a silver nanowire based layer, and they are able to show good performance. I don't know if these are commercially available, but at least prototypes are available. So there is active research in this area, and then hopefully we will see some products come out in the next few years. With this, I think I'll stop. Hopefully I've shown you a flavor of some other applications of oxides rather than just gas sensors. So I'll stop here. Any questions from you guys?
So can you please explain the cathodic coloring and anodic coloring?
Yeah, so let me just go back. So if you see here, you have tungsten that's +6 oxidation state, right? So if I want, this is transparent. If I want this to be colored, I reduce the oxidation state from +6 to +5. So that is a reduction reaction. So that is an example of cathodic coloring. So somehow I need to get electrons into this. If I do the same with nickel, so nickel is +2, so that is transparent. On the other hand, +3 is the colored state. So I'm going from +2 to +3. So essentially I'm oxidizing the nickel. So there I'm reducing the tungsten. So here I'm oxidizing the nickel. So that's an example of the anodic coloring. So those are the two differences. In both cases, there is a change in oxidation state. One is going from higher to lower. This is going from lower to higher. Sure. Yeah.
In the ITO film, the transmission spectra, we see that there is a reduction in transmission in the UV region.
Yeah.
So, what about sunlight? Won't it interfere with?
So if you look at the solar spectrum, you are right. Solar spectrum goes all the way from UV to the visible and a small portion of IR. So you could argue that there will always be some absorption of that portion of the sunlight in the UV region, but again that depends upon what particular application you are going to look at, right? That light will not be visible to the eye. What we really care about in terms of transparency is the visible region of the spectrum, and there it allows light to pass through. Okay, any other questions? Okay, if not, we'll stop here.
Hey guys, we start. Well, yesterday I would like to explain something from yesterday, to repeat it because I think it was not clear at the end. We have seen two proofs. Yeah, I wanted to prove that there is indiffusion. So we were testing two kind of samples prepared in a different way, if you remember. This was the one which is here in the top, was prepared under an atmosphere having hydrogen. In that case, we are creating a lot of oxygen vacancies, so the conductivity was higher. And this one was prepared under an atmosphere of oxygen. Yeah, so we were expecting to have a low density of oxygen vacancies. Yeah, people explains this saying, people who say that everything takes place at the surface, explains this saying that the oxygen attaches to the surface, so we have higher Schottky barriers, and then the conductivity is lower. Yeah. Okay. We want to show that that is not the only thing that takes place. Yeah? So something interesting for the sample prepared under oxygen, if we increase the temperature and then decrease it under vacuum, the sample does not enter with the same resistivity. So something happened to the sample. Yeah, we showed that yesterday. So this is a general idea of what was going on. We can. The fact is that with photoemission we can we can check what the band bending is, looking at the core levels, and we found that the core levels are about at the same place, so the band bending is not different. Yeah, and we made that experiment, which somehow I was upset because here there were not the letters what this is saying. How is my handwriting? After heating, this is B and this is C. Yeah. This is measuring the capacitance. This is second proof we have, or the second evidence to show that something is going on into the grains. Initially, we have this sample prepared under oxygen. Yeah. So we think that the depletion layers overlap, so the whole grain is depleted of grains. So since it's completely depleted of grains, the permittivity is that of the bulk. This is the permittivity I should find. Yeah, we heat it up, and we found a different capacitance. Someone could say, well, what happens here is that something with the temperature is going on. Well, let's cool it down again under vacuum. And very interesting, yeah, the capacitance of the intergrains, which is in this region, yeah, is that corresponding to a frequency of about 10 to the 6, 1 megahertz, does not recover. That is, something happened to the sample. Yeah? And what we think it happened is that oxygen went out, we are under vacuum, we cool down, and the oxygen cannot come back because we are under vacuum. So the grain now has a different density of oxygen vacancies. That is my explanation, what I think is going on. So what I want to say that something is going on in the bulk, not only on the surface. Yeah, and then we made the calculations. The calculations are not easy because we have here a film, yeah, a film over the substrate, and here we have a detail. The capacity is not the capacity of two confronted, yeah, plates, but the plates are something like this, yeah, which corresponds to this metal and this metal, yeah. So, and that capacitance is very difficult to calculate. It's not simple, but it can be done. And this the formula that we can apply, where we have all the details. A is the distance, yeah, which is the separation between the plates, the conductive plates. We have A, we have W, this is the width, A is the separation, or half of the separation, yeah, and we have a logarithm here, and we have L, which is the length, which is this whole. For us, this would be, yeah, the whole length of the plates. We could make the calculations to make some numbers, yeah, and we found what the capacitance of the original substrate is, and amazingly we measured and it worked, so the formula works well. It took me a while to find how to calculate that. It's not usual. People are used to have the capacitance with two plates parallel one to each other, not like this. Yeah. So everything worked quite well, and eventually we could see what was the ratio between the two capacitances. When it's completely depleted, we have the bulk. So we can make just these numbers. So the capacitance of the intergrain, I say, just would be, yeah, what we say, E over D. You know that, no? The capacitance of parallel plates. So in the case we have between the plates a completely depleted, yeah, region, the whole thing behaves as a bulk. So this is the capacitance we should measure. When we developed, yeah, the barriers, this will be the situation. Here is the Fermi level, right? So the region in the middle is conductive. Yeah, so it's like having a couple of plates And instead of having here a whole dielectric, we put in between some piece of a conductor. Maybe you did that in the electromagnetic courses, very basic. And when you do that, it's like reducing the distance between the plates, but this width, because it's a conductor. It doesn't matter where it is. So the net distance between the plates, is what is here is left, this plus this. Yeah. So eventually, because since this is depleted of current, this is which is behaving as a dielectric, and then the net width becomes to be 2W, where W is the width of one of those depletion layers. Do you understand? Is this understand now? So the ratio between the capacitance is directly related. We make the numbers, we replace, the permittivity of the system is the same, the area is the same, so they go away, and all that remains is the ratio between the distance between the plates. This is the distance, the total grains width. And here we have what is effective when we have a region which has a behavior as a bulk, which since it conducts, it does not contribute. It's something like all it does is reduce, the distance, the effective distance between the plates and a regular capacitor. So this is the ratio. And well, knowing all the things, we can calculate what is the width of the depletion region, and knowing that, we can deduce how much is the density of oxygen vacancies. This is what we did, and it worked quite well. Okay, so what we say is taking place if the grains are large enough, or the concentration of donors is not very high. When there is indiffusion of oxygen, what we get is an enlargement of the depletion regions. And if the grains are small enough, or the concentration of donors is not very high, we can have a situation in which we have a completely depleted grain. If that happens, the conductivity of the mechanism is completely different. We don't have those Schottky barriers to overcome. That is why larger grains behave different than the small grains. People are confused with this in the literature. Okay, we saw this yesterday. That is to show you in 3 dimensions. Well, it's 2 dimensions. Grains with the bulk region in the middle, and the concentration of dopants is not very high. We are going to have completely depleted of carriers grain. Okay. We also saw how to calculate some things with using photoemission. We found how to calculate the work function. That is when we send. Let me do it. So suppose we have our work function is 0. That is, this is the top of the. Here is the vacuum level, and we have all electrons here, and we send photons. We are going to take photoelectrons from the vacuum level to a deepness in energy, which is h nu. So we have in our spectrum a width which would be directly the h nu. From this would be the highest. This point would correspond to the highest kinetic energy, and this is the lowest kinetic energy, which is 0. And this width would be exactly h nu. But if the vacuum level is here, and this is the work function, those guys who are here are not going to reach the vacuum level and are going to escape from the sample. So the width of what we see from the electrons, photoelectrons with the highest and the lowest kinetic energy, this width from here to here, is going to be h nu minus the work function, right? I also told you that this works if the work function of the spectrometer is lower than the work function of the sample. Why is that? Because electron can escape, yeah, from the vacuum level, yeah, but this level is close to the sample, as I told you. It's near the sample. If this guy has to go to another place, maybe there the vacuum level is at the higher level, yeah, because this is the Fermi level which is common to everybody. But if it's the work function of the spectrometer, electrons have to go from here to here. But they have almost no energy. They have just escaped from the sample. So it cannot overmount this energy. And if this happens, we are not to measure the electrons we could be measured, that could escape from the sample, yeah, but we are not going to be able to measure it. So the solution to this is to take all this and put a bias. So I'm pushing everything up. Yeah, in that case, all the electrons, if we push this up, this is going to be here, and always we are going to, electrons that escape from the sample are going to go to the spectrometer. Yeah, to understand this clearly, you have to understand very well what the work function is. That is why I was pointing out to that concept. Yeah, you see that and that vacuum level is not a universal level. It's the level close to the sample. Yeah, macroscopically close to the sample. I'll repeat this. I don't know here because it's very difficult, because I don't know you very well. But in my country, people are very confused with the things, so I have to explain it once and again. Okay. So eventually we found that our measures indicate that the band bending is the same. Since the band bending is the same, yeah, the correct interpretation is that what is going on when we do something to the sample is changing the electronic affinity. Yeah, okay. And then yesterday we made the conclusions that the conductivity measurements cannot be explained if we consider only that depends on the height of the intergranular barriers. We saw that in the same intergranular barriers, yeah, for different samples, yeah, the conductivity of those samples can be different. Yeah. So what is written here, experimental results indicate that samples with different conductivities can have the same barrier height. Yeah. But if we consider that the preparation of the sample can change the vacancy density, then if we incorporate the tunneling contribution, everything makes sense. And the evidence for that comes from where? From the measurements in capacitance, as I show you. Yeah? And we saw that doping changes simultaneously explain the change in conductivity and the change in capacitance. Right? This is my interpretation of what's going on. Don't take 100% that for granted, because many people do not agree with what I'm saying. Right? That's the idea of traveling 10,000 kilometers to show you things that are not in the books. These things are not in books. Okay. Well, things are getting even more complicated. I'm sorry. Yeah? People draw Arrhenius plots. What is an Arrhenius plot? You know, can be the conductivity or the resistance as a function of the inverse of the temperature. And from there, they get activation energies and things like that. Right? Well, if we have a sample under vacuum and we heat it up and cool it down and heat it up and cool it down, eventually things are repetitive. Yeah, eventually when we go out in temperature, the sample loses some oxygen, and eventually when we go back, since we are in vacuum, nothing can happen, it cannot recover the oxygen, so things are quite reversible. Yeah. Anyway, if we look at what happens, yeah, see the points. These are the experimental points. There is some curvature, you see. Anyway, people don't care about that, and regularly in the literature, they adjust that with a line, a straight line, and they propose that there is an activation energy. Well, here we have the results for vacuum, and we have the other results. For example, we ended at this point, and we switched to the C point, and open the valves. Now the chamber is full of air. As the air gets into the sample, into the vacuum, into the chamber, I mean, yeah, the resistance changes from A to C. Yeah, so this is conductivity, so the conductivity drops, something which we are expecting. Now we go up in temperature, yeah, and it goes quite close up as it was before, but at some point, look at this, it becomes horizontal. Wow, what's going on there? Something new is happening. Maybe the oxygen starts getting into the grains and the conductivity does not increase as it should. And here there is a competition between a higher temperature. In principle, since things are activated, the resistance is going to decrease, so the conductivity is going to increase, but at the same time oxygen is going into pushing in the other direction, and the competition of those is quite close, so the resistance almost does not change. Yeah, and eventually at some point we decided to go back with temperature, and obviously goes through a completely different path. So something happened in between, and what we think it happened is that the air diffused into the grains and then the conductivity is lower. Well, that is my interpretation. As I told you, many don't think this is going on. I don't know how they explain this. Yes? Well, we also expose the sample to carbon monoxide, but we always see something interesting here. Yeah? This is curved like this. It does not seem to be exactly an activated process. It seems that another thing is going on. So let's try to explain those Arrhenius plots. Yeah? We have an Arrhenius plot should have a linear behavior, and that could be explained very easily if we have a thermionic current, because you know that in thermionic current the conductivity has a dependence E to minus, yeah, the activation energy over kT. So that should be linear if there were a thermionic current. But also something else has to be satisfied. And what it has to be satisfied is that the barrier height has to be uniform. I have never seen anyone but us, my group, talking about this detail. Yeah? And I think that this detail, the uniformity of the barrier heights, explains the curvature. Yeah, people find. And that curvature takes place especially at low temperatures. Yeah, the lower you go in temperature, the more you can see the curvature. This was a sample prepared under hydrogen. Yeah? And in hydrogen we have a larger conductivity because there are a larger number of oxygen vacancies. Without oxygen we can reach this place because we cannot measure below that. The conductivity is too low and what we have is not enough to measure it. Well, how people understand what's going on here? Many papers are in the literature explaining this. And how do they explain this? They explain this saying that the barrier height is not uniform. Yeah? Okay. So if the barrier height is not uniform, why that is going on? Why that is this happening? Well, because we are dealing with a sample having oxygen vacancies, and the oxygen vacancies in fact, cannot be uniformly distributed. So, and this negative surface at the intergranular regions cannot be also uniformly distributed, so we can have some noise there. So it's another one-dimensional problem, it's a three-dimensional problem. So since there are dispersion, what people do? Okay, what do they consider? They consider that they have a distribution of barrel heights. And if this is noisy, and we consider that this comes from noise, it has to have a form of this type. It was a typical Gaussian distribution, typical for things that happen at random. So they say that the barrel heights are not constant, but they have a behavior of this type, having a dispersion, and it sounds reasonable. At first, it sounds reasonable. If you are playing with coins and things like that, you flip coins many times, and then you're going to have a distribution, and the distribution also usually for this type of things have a typical distribution which is Gaussian. Yeah. Well, they say that things go like that, and if things goes like that, the conductance now is not going to be simply that corresponding to one barrier height, but we have a distribution of barrier heights. Yeah. So we have to integrate all the contribution of all electrons passing the intergrain for at different heights. Most of electrons obviously are going to go through the valleys, the region with the lower barrier height. But in principle, we have to make the integration. That is, this is the Fermi-Dirac, which is telling me how many electrons are going to pass through that place, times how many of those heights we have. This is the distribution, the distribution of barrier heights. So the conductivity is going to be the integral of this. Okay. And what is the shape of the integrand, which is this, the product of the Fermi-Dirac function, which essentially is a Boltzmann, and the probability of jumping in that place that corresponds to a specific barrier height. Well, I did it for a couple of numbers that they propose. I'm taking this from the literature. They propose several possible distributions. Sigma, would be the dispersion. And obviously, the larger the dispersion, since this is multiplied by a decreasing function, the product presents a minimum which is more and more on the left for lower values of sigma. So for sigma 0.126, the integrand would take this shape we see here, with the maximum is here, and the larger the dispersion, the maximum would be a lower barrier height. And this is at a not very high temperature. If we go to very low temperatures, 150 K, the Boltzmann factor, which is here, makes that the maximum goes more and more to the left. Do you see that intuitively? That's the way of saying it. Is that your intuition? Let's say it in a different way. Does your intuition tell you that? Okay, as the temperature goes down, the Fermi-Dirac function decreases more steeply, and so the maximum of this product goes to the left. And in this case, for example, 150, the maximum is not even appear. The maximum is at 0. So what this is telling me is, if this is correct, this is what people are saying in the literature, most of the electrons could cross the interface at places where the barrier height is 0. Right? This is what this is saying. Most of the electrons would cross the intergrain where the barrier height is 0. And the barrier height can be 0. Well, yeah, this is what this is telling me. Yeah, that a barrier height with 0, a barrier with 0 height is possible. Yeah, it's not very likely, but it's possible. But I'm not taking into account this specifically. What I care is about the product. So for people who believe in this, at this temperature, most of the electrons would jump, would cross from one grain to another one at places where the barrier height is 0. Well, that sounded weird to me. So that's why I'm repeating it once and again. So we try to make a simple model to see how really the barrier height can vary, yeah, at the intergrain. What do we have? We have positive dopants, which are oxygen vacancies, that have this positive charge in both sides, and at the interface we have the negative charge, yeah, which corresponds to absorbed oxygens. So we put here dopants at random. We expect that oxygen vacancies are distributed at random in both sides, and the negative charge, since it can accommodate easily, we put it in places in line with the dopants. We follow here a previous paper, very old paper, which is fine. Anyway, we check other possibilities and things don't change much. Yeah. So, and we calculated with these conditions, we calculated what happens with the potential. Yeah. And now we don't have a one-dimensional plot. We have a plot in 3 dimensions. So what we are going to find? Something like this. That is, we are going to have the barrier height, yeah, but point by point, here, point by point. And in the middle, at the surface, we are going to have some, yeah, dispersion, because things are at random. Well, if we make a plot for some, say for example this line, we are changing the position along the interface, we are going to find how the barrier changes along the interface. And this is what we obtain. Okay. There is some random, yeah, here some dispersion. Well, you can run this many times. You're never going to find a place with a 0 barrier height. Why is that? Because this is not exactly a random, yeah, like throwing away a coin and finding solutions. This is not like that. We are summing, yeah, we have to sum to get the potential any point, you have to sum the contribution of all the positive and negative charges. And when you do that, yeah, you're never going to find a place with a 0 potential. Yeah, because the contribution of every charge is kind of 1 over r, yeah. And when you sum up all of them, there is no way to find out that. That is, maybe a Gaussian distribution is good for small values, or it can be a good approximation if you are not taking into account that you have this factor here, yeah, the Boltzmann factor. So this is what really happens, not a Gaussian distribution. As a consequence of that, here we have the detail. Look here. If we see it in a linear scale, the line, the full line, corresponds to a Gaussian distribution. And what we found doesn't have a Gaussian distribution shape. It's the one with the points here. You see? Somehow it's skewed to the right. Yeah? It extends more to the right and to the left. It's not exactly symmetric. But that is not the most important point. The most important point is that, see here, this is in logarithmic scale. We go to 10 to the minus 15 and 17. Yeah? Our distribution reaches this point and there are no points below that. it collapses below that. And the shape is completely different. And why do I'm plotting this in logarithmic scale? Because we have another factor here to take into account, and that other factor is the Fermi-Dirac distribution. Yeah, and when we multiply, yeah, P of psi, yeah, the probability density for the barrier heights, times the Fermi-Dirac distribution, from here to the left, in the real case, the product is going to be 0. But for these guys, it's not going to be 0 if you take into account this distribution, the Gaussian distribution. And at low temperatures, not only that, the main contribution is going to be here. Yeah. Where in fact, in real life, here we don't have any contribution of any type because there are no barrier heights of that size. So here we have the conductance, that is this product, that is the integrand for the real distribution, or I don't know, well, I wouldn't say real, I would say from our model, but a model, a reasonable model. Yeah, and when you do that, you see that yeah, you have, yeah, here it collapses. We don't have places where the barrier height is lower than, say, 0.55 eV, yeah, even though the average barrier could be of 0.8. We don't have anything below that. So this is the distribution of the integrand. And if we go down in temperature, yeah, it's always the same. Below that we have nothing, and the distribution becomes narrower because the Fermi-Dirac function drops very fast, and at low temperature, yeah, it goes faster. Yeah, but this is what's going on in opposition to this. Yeah? And even this, 100. Look at this. This could be the integrand at 150 K. You see the shape? And the shape coming out of our modeling is the one we see here. It's completely different. Yeah? And of course, most of the electrons don't cross the intergrain at 0 height of the intergrain because there is no barrier, there is no place where the barrier has 0 electron volt. Yeah. Okay. So how can we explain that the experiments show in an Arrhenius plot show some curvature? Well, it's much more easier without doing much, without making things more complicated, by considering the tunneling contribution. I'm the tunneling man, yeah? I like tunneling. So if we take into account tunneling current naturally gives this curvature, yeah, results. We have here are some theoretical results, see, for different dopings. The higher the doping, the narrower is going to be the barrier. The narrower the barrier, the contribution of tunneling is going to be larger. And this is what we see. Yeah. Yeah. The conductivity increases. And these are the experimental values that I plug in here. I did not try to fit them, but it's very easy to see that some value about 5 10 to the 24 and 1 10 to the 25, say close to 1 to 25, maybe I could have choose 9 10 to the 24, I could fit very well these results. I did not try to do it, I just comparing. And see here, this is the other case for oxygen. And for oxygen, we said that the vacancy oxygen would be lower. And see, for lower doping, it fits quite well. Yeah? Well, this is another piece of information saying that tunneling is important in these things. Okay, then conclusions of these results. Fluctuations of barrier heights at intergranular surfaces do not present the Gaussian distribution. Yeah? adjusting the height of the barriers with a Gaussian leads to an artifact. You know what an artifact is? Yeah? And if we take into account tunneling current, yeah, if tunneling current is the dominant conduction mechanism, then we observe the right dependencies without resorting to anything else. Okay. Yeah. Sure.
The barrier heights should be different for different kinds of grain, and it should depend on how much oxygen is present.
Yes, we assume that the surface is behaving always about the same. Yeah. For small and large grains. You mean there is a difference? Well, we could have different surfaces with different orientation. That could change a little, yeah. But
this is polycrystalline, so we have
yeah, but essentially we are studying just one interface, yeah. And people are propose this, yeah, propose that that this curvature can be explained resorting to this hypothesis, which I think is, in principle, is not right. I think in principle sounds it makes sense at first sight, because you're saying, okay, I have noise, the distribution of charge is only uniform, so I'm going to have some dispersion in the barrier heights. So if you have a dispersion in whatever, what is the usual regular distribution you use? The Gaussian distribution. Well, let's use the Gaussian distribution. But they did not analyze the details of that. And the details on that is that the way you integrate, you don't have also the Gaussian distribution. You have the Fermi-Dirac distribution. Really, they are involved. And this product is what counts. Yeah? And it happens that maybe things are not so bad if you see this. Look at the distribution here. They don't look so different. Hey, come on, it's a very good approximation. No, it's not a good approximation for our case, because things happen here. And even though they look that they go to zero in a linear scale, they don't go to zero. Yeah, they are important. They are important because they are multiplied by the Fermi distribution, which goes in the other direction. So I think the results they found is an artifact. They are not real. It's a bad approximation. In this case, that's not work well. Yeah? And you see, my task is to destroy others' proposals. Yeah, others' models. Okay. Well, things are getting even more complicated. So far, we are dealing with parabolic barriers. That is what everybody says, except an old guy, an old paper I found once, that it was saying that maybe that was not correct after all. And in fact, I think he could be right. And the analysis is the following: how a defect forms at the grain. We have an equilibrium, essentially. If you are in equilibrium, this is an oxygen in the crystal. If an oxygen leaves its position to eventually leave a vacancy there, yeah, that oxygen has to go to the surface, and the surface find another oxygen and dissolve. Yeah, and this mechanism, this reaction has to be equal in equilibrium to the opposite reaction, where an oxygen absorbs, diffuses into the bulk, and occupies the site of a vacancy, killing the vacancy. Yeah, everybody agrees on this. Yeah, and this process involves many different processes, what I have just been telling you. First, the oxygen, yeah, which is in the crystal, has to leave its position, leave in a vacancy. The vacancy immediately ionizes, yeah, leaves 2 electrons, and the oxygen that leaves its place had to be an interstitial oxygen, which is doubly charged, that interstitial oxygen must reach the surface, yeah, and when it reaches the first surface, it becomes surface oxygen, yeah, an ion absorbed on the surface, and then eventually that thing becomes neutral, and this neutral has to find another oxygen, and eventually dissolves, leaving the site free. Yeah. Well, this is what's going on. Everybody agrees in these processes. And if that is the case, well, we can apply the law of mass action. Yeah, in this reaction. Yeah. What we have in this reaction, we have the vacancy, the electron concentration, and the pressure of the oxygen in the atmosphere. And these are the oxygens at the regular place. This almost does not change. Yeah, because the number of vacancies is small compared to the number of regular oxygens. Regularly, the sites are filled with oxygens. Yeah? We used to say in Spanish, I don't know if you say that there is a limit to the number of holes a cheese can have. You see that cheese can have holes. You cannot have more holes than cheese. Yeah? Do you say that here? No. But here's the same. We cannot have more vacancies than places we can, yeah, we can take oxygens. Okay. So if we apply the law of mass action, we have the density of vacancies. There was the electrons, 2 electrons, so it's n2 square, and we have the pressure, which was 1/2, so it's pressure to 1/2, and that has to be essentially constant, because the density of oxygens in their places is practically does not change. Well, this implies that for a given gas pressure, we have a given gas pressure. This product is constant. Do you agree? The product of the vacancy density times the square of the electron density has to be constant. Look at the equation. If this is constant, I don't change the pressure. This is a constant, so this has to be a constant. Yeah? But we know that the electron density changes along the depletion region. Why does it change? Because the distance between the bottom of the conduction band and the Fermi level changes along the barrier. The barrier is like this. Yeah? Here's the Fermi level, and this is C. So this distance changes along the depletion region. So N has to be decreasing, yeah, along the depletion region as we reach the surface. So if that is the case, V has to increase as we reach the surface. It's very basic, isn't it? So we can then deduce that the vacancy density increases exponentially as we reach the surface. It increases like this. So, and the density of vacancies is essentially the density of dopants. Yeah. So essentially, if ND was the density in the bulk, here was the bulk. As we go towards the surface, the density of vacancies is going to increase. Well, and now the potential is no longer parabolic, does not have a parabolic shape. We have to integrate this, which is not very easy, but it can be done. And the potential has this shape. Yeah, it's quite weird. Natural logarithm of 1 plus the tangent square. Yeah, it's quite complicated, but I can show you how it looks. Okay, this is what happens. The first plot on the left is showing what happens when you have a parabolic, yeah, barrier that corresponds to a constant density of dopants. That is a constant density of oxygen vacancies. Well, on the right, we have to start the donor concentration through the depletion layer if the donors are mobile. That is, if they can reach the equilibrium distribution. And it's amazing that it goes, you see, it explodes. can go very high. I did that for single charge dopants or doubly charged dopants. And the form is what we said. The form is exponential. This is the concentration of oxygen vacancies. Those are the dopants. And the form is an exponential. Well, we have to integrate that twice to get the shape of the potential barriers. And the shape of the barriers can be really very different. This here in dashed line, we see the barrier corresponding to a constant doping. This was done at regular temperatures and regular dopings people are proposing in the literature. So the electric potential for a constant doping is something that grows, increases very nice, parabolic shape. But if donors are mobile and they can find the equilibrium, the form is called Go-Chapman shape. This is the dotted guys. We have included, this is a detail, we include an elastic contribution. That is, since at some point the concentration of dopants were going too high, we said, well, come on, this is going up, it's coming out from the theory, but in fact, in real life, this cannot happen. I cannot have more holes than cheese. It is something has to stop this process. So we look for different processes. And a process will look nicely, we find the literature, with the fact that vacancies interact among themselves. So if they are very close, the total energy starts going up, and that would be a way to stopping the formation of vacancies. We included that, and it changed significantly the density of vacancies, but it did not change significantly the shape of the potential. The potential is really very abrupt. See, here we have the straight line and the dashed line corresponding to the solution with or without that elastic contribution. So instead of having now parabolic barriers, we have something which is very abrupt. Goes at the beginning, it goes like a parabola, but then it goes up very fast. So if that is the case, you're going to see, you can imagine immediately a double barrier for this case. Could be amazingly narrow. So the contribution of the tunneling would be even much larger than we thought. Okay. So here we made some calculations to see what would be the sensitivity for different barriers. And we found that the shape of the barrier is going to control the sensitivity of the sensor. For example, here we have the conductivity. This is a logarithmic scale as a function of the barrier height. This is the typical temperature used in sensors for different dopants, for different dopant concentrations. And we see that as this what we have here is 10 to the 22. Here practically there is no contribution of the tunneling. As soon as we go to 10 to the 23, we see a small difference. Tunneling appears, and then it goes up very fast. But essentially, even though we have a important tunneling contribution, essentially the slope of this does not change much. So the sensitivity is going to be reduced as the doping becomes higher, but the effect is not going to be so terrible. However, if we adopt the Go-Chapman barriers with that different shape, tunneling immediately has a very strong contribution. And we have here the same for the same plot for the same dopant concentrations, the same doping. But for Go-Chapman barriers. And from one case and the other, we can calculate the sensitivity. And what is the sensitivity? Well, for the parabolic barrier, as we saw, for low dopings, mostly nothing, it does not change much. It's reduced a little when we have a very high doping, yeah, 10 to the 25. But things are not so bad. But for the Gauss-Chapman barrier, the sensitivity collapses, yeah, as we go high in doping. We're defining here the sensitivity as a function of the barrier height, yeah, with how the conductivity changes as a function of the barrier height, yeah. We are doing respect of logarithms. That's why 1 over g, the derivative of g over phi. So as you see, these barriers are not so simple, and you have to be careful. There are many things can be taking place, and you cannot disregard it as this is a good approximation. Be careful. There are exponentials and logarithms involved, and there are functions which are not intuitive. Yeah? Okay, then conclusions. If vacancies can diffuse, the equilibrium distribution leads to non-parabolic potentials. Yeah? We have included elastic interactions to limit the density of vacancies, but in principle the resulting potentials are not seriously affected. Yeah? It's important not to say something which has no sense, yeah? To arrive into a situation in which we have more vacancies than atoms available. But the voltage, the barrier does not change much. And we found also that the sensitivity depends a lot on the barrier height, and also depends on the shape of the barriers, not only the height. Right? I think that this could be one of the reasons, if not the most important one, why people are finding so different results, and why results depend so much in the preparation, because in preparing the samples, you have different density of doping, they were prepared in different ways, they came from low temperatures, they anneal the samples, others do not anneal it, yeah? And the results are very sensitive to all those details. Yeah? Small changes in the dopant concentration can lead to completely different behavior. Okay? Okay. Oh, I should go.
Celso, sorry, two questions.
Oh, sure.
So we're talking about non-parabolic potential. Right?
Yeah.
So I'm just thinking, is this similar to, for example, if a PN junction? Initially, we assume that in the depletion region, the concentrations are constant. That gives you your parabolic.
Exactly.
But in reality, that's not true because you have diffusion. So you assume a linear change in concentration. Is that?
Yeah, it is related to this. Yeah, what I said at the beginning of these courses, I think I said this on Monday. In electronics, the doping is not a subject. That is, you ask for silicon or for gallium arsenide with a specific doping, you get that from the guy who fabricates those things, and you don't care any longer about that. The doping is that, and that's it. And you create you make interfaces, and you make diodes and transistors, and the doping is the one that the guy who fabricated the substrate has. So that's not an issue. But here it's a key issue, because the doping can change, because oxygen diffuses a lot, it moves, things are mobile. You don't know what is the doping and initially, and you don't know what the doping at the end of your experiments, and that's what makes us, I think, very confusing all this. And people obtain very different results. There's a bunch of contradictory results in the literature. Yeah. But it's correct what you say. That is, I have seen in books that this analysis, if, for example, if it were constant and they propose a linear increase of this typical, and you get there that the potential, if I remember well, does not go to the square but to the cubic of the depletion region. Yeah, we can make those numbers. Well, I prepare a problem for tomorrow, calculating how goes the barrier height with the dopant concentration. Okay. Okay. We'll try to start. Just give me 15-20 minutes and we're done. The first part of this, because if not, I will have to cut in two pieces something which is important. Those who were in my talk, one was the day before yesterday in the afternoon. I'm going to repeat some things, but I think not everybody went to the talk. I will try to be more academic, to do it slowly. Yeah, that's supposed to be more a presentation. Yeah. Okay. We are going to see the sensor power law response. That is how the sensor responds to the gas pressures, which eventually what we care in sensors. That is how they respond if I put more or less oxygen, more or less carbon monoxide, or whatever. Yeah, and people found that the response to the pressure of different gases, yeah, goes like this. Yeah, it presents a power law. That is the conductivity of the film is proportional to the pressure of the gas to some exponent. I can define with minus or plus. Then it's not very relevant. If that is the case, then the exponent gamma, yeah, you can derive from here. The exponent gamma is the derivative of the logarithm of the conductivity with respect of the logarithm of the pressure of the specific gas you are testing. Yeah. So what we are experimentally, what we see or what we have is here we have the sensor film. Here is the gas, and as a consequence of the presence of the gas, yeah, what is going to change is the conductivity. So you must need an electrical circuit to measure that, to measure how the conductivity changes, and eventually you're going to have a response, and that is what you want to have. So this gamma somehow measures the sensitivity of the sensor, and since this is what we have regularly, this gamma, this exponent, has to have this relationship with the conductivity as a function of pressure. People write this as we see here. Yeah. Somehow you multiply and divide that differential of Vs. Vs is the height of the intergranular barrier. So and then we can write things in this matter, this way. Okay, I will leave this as a problem for tomorrow, to derive this from this. It's very easy, that is. Yeah, and in that way, you can see that the exponent is the product of two factors. Yeah, this second factor is called the reception or receptor function. It is telling me how much the barrier changes as a function of pressure. Yeah, is related to this. How changes the barrier height. And the second function is called the transducer function. How that change in the barrier height, yeah, makes a change, produces a change in the conductivity. So this is called as transducer, yeah? And this is the receptor. Okay. So as we have seen, if a molecule adsorbs on the surface, if we have oxygen in mind, it produces an acceptor state at the surface, so it captures electrons from the conduction band, and the band bending, yeah, Schottky barrier emerges. All right? And this last level is called LUMO, which is last unoccupied molecular orbiter. That for oxygen is in the mid gap, and so that's the reason why electrons go there. Typical people accept that it's about 1 electron volt below the conduction band for tin oxide. Yeah, for tin oxide. So this is an N-type. I took an N-type semiconductor because tin oxide is an N-type. As we said, the band bending is produced because we have acceptors here, acceptor levels. This is acceptor level. And electrons from the conduction band have to go and jump here. Yeah? Well, it says here, an acceptor state can be occupied by an electron from the conduction band and gain an extra energy. The extra energy that gains is the distance between here, where they go. He were mostly at the bottom of the conduction band, going to here at the acceptor level. So when the oxygen absorbs here, not only you have to take into account the absorption energy because the oxygen absorbed there as an atom, but it gets another extra energy. That extra energy that it gets is the energy that the absorbed oxygen gains if he gets an electron from here. He gets this extra energy. Why? Because now the electron was before here and now it's here. So as a system, that oxygen gains an extra energy. And that extra energy, as you see here, is the energy of the conduction band here in the bulk minus the energy of the acceptor level here at the surface. So the total energy of absorption in the literature, I'm using the letters used in the literature, is Q0, which is the energy just due to the absorption of the neutral oxygen plus this energy if it is ionized. Right? So you already know all this, band structure and how things go. So I will talk briefly of the Falkenstein theory of adsorption. For those who were not at the talk, Falkenstein was a Russian theoretician who was working in catalysis, and the whole community of sensors researchers had not paid attention to him. Well, I think they should have paid attention to Falkenstein. Falkenstein was studying catalysis on semiconductors, and he realizes that catalysis on semiconductors is very different than catalysis on metals. People working in catalysis are used to work on metals. Metals are the catalysts. They don't use semiconductors, and they are scared of semiconductors because usually people working in those fields do not know anything about semiconductors, and that is very confusing to them. But this guy decided to work on that and made the theory of catalysis on semiconductors. His books and his papers are terribly boring, terribly difficult to read. It took me quite a while to understand what he was saying, but I can tell you that I think he was right. He was very smart. So I decided to incorporate his ideas to understand how sensors work. Well, and the guy was saying things that are quite reasonable. Like I say, the rate of, we are going to do this with non-dissociative absorption. That is, non-dissociative absorption as I'm considering that the molecule or an atom absorbs on the surface, and that's it, and it dissolves as it absorbed. Yeah. This was done by Falkenstein. Yeah? I'm repeating what he did. So the rate of absorption, in the surface, has to be proportional to the number of atoms that are impinging on the surface. And from the kinetic theory of the gas kinetic energy, it's very easy to know that this is this. Yeah? That the number of atoms that are landing on the surface proportional to the pressure, inverse proportional to pi, the mass of the atoms kT. Yeah? This is not difficult to know. And also the number of atoms that are incorporated on the surface has to depend on the number of of sites which are available. And we are going to define that 1 minus theta, where theta is the coverage. Yeah, if the surface is completely covered, we have no sites where to land. Yeah, the atom. Well, don't worry about this theta. We pronounce it theta, the Greek letter. Coverages are going to be very low, so this is going to be always about 1. And also we have the sticking coefficient. The sticking coefficient is the probability that an atom landing on the surface is going to stick there and is not going to bounce and come back. Fortunately, in our case, in the surface we are studying and the gases we are studying, the sticking coefficient is practically 1. That is, all of the atoms that are right to the surface, they stick to the surface if they find an empty, a site which is empty. And since most of them are empty, fortunately this is not so complicated. Well, once absorbed, in principle, we can consider that all the absorbed particles, I have oxygen in my mind, but all the absorbed particles can be dissolved. And particles at the surface, as we saw before, can be charged or can be neutral. Yeah? When I found this for the first time, I saw, why didn't I think on this before? We can have neutral or charged particles absorbed. It depends where the Fermi level is, respect to the absorption site. Well, no one pay attention to that. This is not in the gas sensor literature. So he said, Falkenstein says, well, neutrals, this is the concentration of neutrals. Theta 0 would be the concentration of neutrals. Time then, and asterisk is the density of absorption sites, times the number of times that the oscillation frequency, number of times that the atom tries to escape on the surface. This typically, they take 10 to the 13. I learned that from chemical engineers and chemists. And also we have a barrier, which is the energy at which that atom is absorbed on the surface. That's an exponential. And this was for neutral absorbed particles. And if the particle is charged, we will have the same, the number of sites, the density of those, the frequency, number of attempts per unit sec, per unit time. But to escape from the surface, if we are dealing with an ion and not a neutral particle, we have to sum up to the energy, the absorption energy. We have to add up the energy needed to get rid of the electron. Yeah, what we call delta E. To this energy from here to here, we have to get rid of this electron. So this is the situation. Yeah, and in equilibrium, the frequency of the rate of absorption has to be equal to the rate of desorption. Yeah. Okay. What is the occupation probability of the surface states? Well, that is given by the Fermi-Dirac function. That is the ratio between charge absorbed particles with respect of the total number of particles absorbed. Is going to be just a factor given by the Fermi-Dirac distribution. Well, with the previous three equations, we can put them together and deduce the absorption isotherm. Yeah, the isotherm is said at room temperature. What is the coverage as a function of pressure? You have to deduce that. Yeah, this is the Chanel form. This is the Langmuir absorption. Langmuir, that's what chemists call it. At this, Irving Langmuir, right? So we can deduce everything. I'm not going to make the algebra. You reach something which is beta p plus over 1 plus beta p, where beta have this shape, this form, and beta 0 is this constant that depends on the energy of activation to extract the atom, the temperature, the density of available sites, and the frequency and the sticking coefficient. So we arrive to this form. But if you see this, see in the denominator you have 1 plus nu minus h 0. This is about 1. That is the number of atoms per unit time is about the same for charge of neutral atoms. But we have here the exponential of FCB minus F over KT. And this is a very small number. This is the energy I need to, essentially to extract those ions from the surface. This can be a very, very small number. So essentially, this is not here. This is we can neglect this term. Okay, that would be the situation if both kind of absorbed particles, neutral and charged, can be dissolved. But if only neutrals dissolved, so the gas particle in the gas absorbed at the surface, neutral, and then charges. Yeah, and these things are in equilibrium, but this jump is very unlikely. This is what comes out from this theory. This beta, which is here, reduces to this form because it's essentially zero, so it reduces to this form, which is much more simple, much more simpler. Okay, we extended this work of Falkenstein. This is ours. Well, it was not a great well work, but we did it. Yeah, we extend this to dissociative adsorption. Let's suppose the molecule goes to the surface and dissociates. We are thinking in oxygen. It's a molecule and dissociates. So to extend those results, it was not very difficult. That is, the number of molecules, yeah, that comes to the surface per unit time is the same than before. But now, since we have two atoms, we have to have two places together to accommodate the both atoms. So we need 1 to minus theta to the square. Anyway, this one was going to be 1 and the sticking coefficient 2, so it's not a problem. And now the sorption can take place in 3 different ways. That is, neutrons are going to desorb as before. Now it's a second order reaction, that's why the coverage is to the square, because we need 2 atoms on the surface to go together, so it's a second order reaction. 2 ions can come up together, yeah, and here we are going to get rid of 2 electrons, so that's why we have a 2 here. And also we can have 1 ion, 1 neutral, yeah, to go together and dissolve, and to do that they are going to get rid of only one of the electrons. Yeah. Well, with these equations we arrive to this, to the coverage as a function of pressure, which adopts this form now. We have a square root there. I don't know if you have done this in some course in this is typical in chemical engineering. Yeah, and things as before, they are not exactly as before. They appear as squares because we are dealing with this with dissociation. Yeah, it's a second order reaction for desorption. Yeah, and we also have to remember what is the charge density in the depletion region. In the depletion region, we are adopting a parabolic shape. And now you can say, why do you adopt a parabolic shape? Well, we have to start with something. So let me adopt a parabolic shape. It has this form, and the charge density at the grain is this one. Is the density of charged particles. In fact, this is a percentage of per 1 times the number of sites where particles can be adsorbed, and this goes to twice the charge of an electron, assuming the oxygen absorbs doubly charged. There was a paper, it took us a while to publish in Sensor Actuators B, which is a very good journal in this topic in sensors. Okay. Well, the next step was to reduce the problems. I'm going to end up with this. The next step is to reduce the problems because you see that things are very complicated. So we are going to make an experiment we are going to do with the results because so many things to take into account that it's a problem. So the first thing we have to get rid of is the fact, and since people do not believe us that the tunneling current could be the main contribution in the conductivity, was to get rid of that problem. Yeah, and how did we do it? Well, we take very, very small grains. If the grains are very small, we don't have room to have band bending. So, and if we made the calculation, really it's quite negligible. The band bending for grains of 5 nanometers of diameter. So we try to create this kind of films of very small grains. So, and very small grains, the conductivity, we don't have barriers. After talking of barriers all this time now, we're going to get rid of the barriers. So things are flat now, if this situation originally, suppose with not without states at the surface, at the intergrains, so at the surface of the grains, the Fermi level is to be high. This is going to be an N-type material with a lot of conduction electrons here. Yeah, this is one-dimensional model. I should have maybe draw a sphere, but it's the same. We are looking for general relationships, and this is easier, and it's easier to understand. So here we have the Fermi level, here the doping level. So if the distance is large enough, most of the dopants ionize, so they contribute to the conduction electrons density. And if we put some, I'm thinking in oxygen, some absorption, some acceptable levels at the surface of the grain, most of the electrons that were in the conduction band drops there, yeah, and there remain just a few percentage of what we had before. But they are very important. This conduction electrons are very important. Why? Because the conductivity is going to be controlled by the density of these conduction electrons that remain there. Yeah. Now we're going to have barriers, intergrade barriers, so we're going to have another grain close to it, and the electrons are going to flow from one grain to another freely because there is no intergrain barrier. Yeah. So, as it says here, in very small grains, band bending is disregarded. And there are most electrons due to neutrons are trapped on surface states, but not all of them, most of them. And the conductivity is going to depend directly on what are the density of those conduction electrons remained there, the conduction band. We are going to build on this. I think it's time to finish for today, but we are going to build on this, yeah, to see and to derive what is going to be the dependence, what the dependence should be as a function of the present gases, yeah, in the ambient. So we are going to do that tomorrow. As soon as we end with that, we are going to make an exam. An exam. Yeah, we're going to do an exam together. So I'm going to present type of exams I used to take with my students, and we have to solve it together to see if you just have understood something of what I try to tell you. Right? It's very, no, don't be scared. I will do it here, as Professor Rahman did it. Yeah? Well, okay. That's all for today. Thanks a lot for your attention.